This is video number 50 in our series Electrical Circuit Analysis. A reminder that the playlist for all the videos is at the website digital-university.org. Okay, what we want to do in this video, we're considering the same circuit that we solved in video number 49, that is, determine its Norton and Thevenin equivalent circuits. What we did in the last video was we first determined its Thevenin equivalent circuit, then just did a simple source transformation and obtained the Norton equivalent circuit of this. Now, in the Thevenin equivalent circuit, we have this voltage here of 6 volts. That's the same as the open circuit voltage here across the terminals AB. That's this open circuit voltage right here. The 1.2 amps, the Norton equivalent current, if we put an ammeter across these terminals, that's what that would measure, is 1.2 amps. And we can see that in the Norton equivalent circuit, it would have an open voltage of 6 volts from 1.2 amps flowing through the 5 ohm resistor. Now, this 5 ohm resistor, this is, you can call it the Thevenin resistance or the Norton resistance. It's the same in each case. And as you saw in our previous video, the way we determined that value was, as you same you do for any other circuit, remove any current sources or any voltage sources. Here we just had a voltage source, so imagine drawing a line through this. And then what we did after that was we determined for the remaining circuit, we determined the resistance of that circuit as that would be seen across these resistors or across these terminals AB. And that we determined to be 5 ohms. Now what we're going to do in this video, instead of determining first the Thevenin equivalent, suppose we wanted to determine the Norton equivalent first, and then determine the Thevenin equivalent circuit. That's what we're going to do. We're not going to rederive this value of 5 ohms because that's the same as what we did in the previous video. But to proceed then, right from square one, look at this and ask ourselves, what would be the Norton equivalent of that? That is, we've already determined that we have an equivalent resistance of 5 ohms, but for the Norton equivalent circuit, what current source would it have? And that would be the current across here if we just put an ammeter across these terminals. And we can see, we can determine that, but that's going to be a little bit of work because we can go to here now. When we put an ammeter across here, schematically that's just the same as drawing a conductor there and asking ourselves, what's the current flow across that conductor? Well, we can find that out, but it's going to take a little bit of work because we're going to have to consider 3 separate loop equations now. Here would be the first loop equation with current 1, and then here would be the second one, I2, and the third one, I3. Now, as you saw us doing the previous videos, we're assuming that all of our loop currents have a clockwise direction to them. In reality, some of them may be clockwise, some of them may be counterclockwise. And as you saw in the previous videos, when we determine a numerical value here, if it comes out negative, then that means it was not going clockwise, it was going in the other direction, and we can adjust it accordingly. But okay, we want to determine then, well, here we have three separate currents, I1, I2, and I3, but the ones we're interested in, of course, are I2 and I3. What is the flow across these terminals here? But let's take a look. We'll start with loop 1. And here, let's look at the 6 ohm resistor. Here we have the current going down like this, going from plus to minus. So it's minus 6, and the net current flowing through it is I1 minus I2. So that would be the voltage drop across the 6 ohm resistor. Then here we have minus 3. Then the current flows from plus to minus of I1 minus I3 for that voltage drop. Then here, the voltage drop, if you will, for the voltage source goes from minus to plus, not plus to minus, as we're doing for these resistors. So this is plus 72. And adding them all up by Kirchhoff's law comes out to 0. Now, let's look at loop 2. Here we have minus 6, I2 minus I1. And then minus 12 times I2. That equals 0. And then for loop 3, minus 3, I3 minus I1. And then minus 4 I3 equals 0. So here we have three unknowns. I1, I2, and I3, three unknowns, three separate equations. So, in theory, we should have enough information to solve for all of them. We're just interested, though, in I2 and I3. Now, if we look here at this equation and just do some very simple algebra with it, what we come out with is 9 times I1 minus 6 times I2 minus 3 times I3 equals 72. So that's what we're going to write in place of that. And again, that's just very simple algebra involved there. So here we have 9 times I1 minus 6 times I2 minus 3 times I3 equals 72. Now, from loop number 2, we can multiply both sides of the equation by negative 1, make these plus. We'll have minus 6I1, 6I2 plus 12I2, that's 18I2. And we have nothing for I3 from there, and that equals 0. So we can carefully erase this so we don't mess up this equation. Okay, and from loop 3, multiply both sides by negative 1, minus 3I1. There is no I2 there. And 3 plus 4 plus 7I3 equals 0. Okay, now, again, three unknowns, three equations. We want to determine I2 and I3. That's the extent of our interest. And remember what we did in the previous videos. We can solve these using matrix determinant methods. Step number 1, take the numbers in the I1 column, the I2 column, the I3 column, and we get this matrix. And then minus 6, 18, 0. And we want the determinant of that matrix. And you can expand that using minors. We've gone through it in previous videos. Won't go through all the steps here, but we get an answer of 720 when we do that. So here we have, and this is important, we're going to use this to determine I2 and I3. And if we wanted to determine I1, we would also use this number too. So the determinant of this basic circuit matrix is 720. Okay, now we want to determine, let's see what I2 is. So the way we do that, as you saw in the previous videos, I2 equals, in the numerator, we would want to know the determinant of this matrix. We keep the I1 column, the I2 column gets replaced with this, and we keep the I3 column. So we have 9 minus 6 minus 3. This gets replaced with this, and the I3 column stays the same. We want to know what is the determinant of this 3 by 3 matrix, and it has to be divided by this, the determinant of our basic circuit matrix. And again, we're not going to go through all the calculations here. It's pretty straightforward. But when we do it, we get an answer here. This equals 4.2. And that is for I2. So here we have 4.2 amps in that direction. Now, what about I3? Let's just set it up. It's the same kind of deal. To determine I3 for the matrix that we use up here in the numerator, the I1 column stays the same, the I2 column stays the same, but the I3 column gets replaced with this column. So now we have 9 minus 6 minus 3, then minus 6, 18, 0, and replace 72, 0, 0. And we want to know what is the determinant of this matrix, and then divide that by, again, 720. And when we do that, we get an answer of 5.4. So that's what I3 is. I3 going in this direction. Okay, and again, we went through this pretty fast, but again, we've done it so many times in previous videos that hopefully it's familiar territory to you by now. But let's get rid of this. So, the net current, the Norton equivalent current, will be 5.4 minus 4.2. 4 minus 2 is 2. 5 minus 4 is 1. So that, going back to our original circuit, here, if we put an ammeter across here, the current it would measure would be 1.2 amps. That is the Norton equivalent current. And that's what we determined it to be before in the previous video. Only there what we did was we first determined the Thevenin equivalent circuit, then use a simple source transformation like you saw in video number 22 to get this answer of 1.2 amps. And actually that's the smarter way to do the problem, because to go from here to here is pretty short to go from here and determine the Norton equivalent current. As you saw, it took a bit of work because we had to deal with 3 separate loop equations. But if we started the problem from here, then we'd say, all right, we know what this is, and as you saw us do in the previous video, we're not going to repeat it to determine the Norton equivalent resistance or the Thevenin equivalent resistance to the same thing. Remove whatever current sources, whatever voltage sources you have. We can remove the voltage source just by drawing a line through it, so it's no longer there. And then we ask ourselves, for this circuit, what is the resistance of it as seen across these terminals? And that's the same procedure whether you determine the Thevenin equivalent circuit first or the Norton equivalent first. It's the same procedure. We did that in the previous video, so we're not going to repeat it, and we got an answer of 5 ohms. See, when he had to do the same thing here, we get the same answer. So you'd say, all right, our Norton equivalent circuit then would be, now at the Norton equivalent circuit we have a current source. The equivalent resistance is in parallel with that. And then we have our terminals. So then we would have determined, all right, this is our Norton equivalent circuit. Now, once you know this, what would be the Thevenin equivalent circuit? Do a source transformation, as you saw us do in video number 21, where that would be a voltage source, and this resistance that's in parallel to the current source is in series with the voltage source. And what is the magnitude of that voltage source? This times this, 6 volts. And that would be the Thevenin equivalent resistance. So you can see that, hopefully it was worthwhile that when you have your problem and you ask about equivalent circuits, think about it. Which is the easiest to determine right away? The Thevenin equivalent or the Norton equivalent? Doing a little bit of thought can save you a lot of work. Okay, that's it for this video. We're going to have one more video like this for equivalent circuits. It'd be another bridge circuit. But now, here, we were putting the load resistor across these terminals. Well, in the next problem, there is a resistor here, so we're going to put the load resistor across here like this. And then we're going to ask ourselves, for this circuit, what would be the Thevenin equivalent of it, and what would be the Norton equivalent circuit of it. So come back, join us for that video, and let's see what kind of a solution we get to this problem.